Hello students, in this video lecture I am going to discuss the relation between a lattice and a complete lattice. Now before I actually come to discuss and I actually start with what the relation is between a lattice and a complete lattice, let me just recall the definitions of complete lattice and the definition of a lattice. Although these definitions have been discussed in details along with examples in my earlier videos, but for the sake of this video, let me just recall the two definitions. Now a PO set P less than equal to is said to be a complete lattice if whatever subset S of P we may take, if we are able to find the join of S and the meet of S, in that case the PO set P is said to be a complete lattice. This was one definition that was discussed already. And now coming to the second definition, when is a PO set P less than equal to said to be a lattice? Now a PO set P less than equal to is said to be a lattice if whatever elements x and y belonging to P we may choose, if we are always able to find the join of y, x and y and the meet of x and y, if both join of x and y and meet of x and y exist in that, and if this happens for every pair of elements x and y that we choose from P, then the PO set P less than equal to is said to be a lattice. As I already said, since these definitions have been discussed in details along with the examples in my earlier videos, so if one is interested in knowing more about lattice and complete lattice, you can go and refer to those videos. But in this particular lecture, I am going to discuss what is the relation between the two. What is the relation between a complete lattice and a lattice? Now the relation which we have between a complete lattice and a lattice is that given a complete lattice will always be a lattice. This is what I'm claiming. Now let me just prove this claim that a complete lattice is always a lattice. Now if P less than equal to is a PO set that is given to you, and let us suppose that this PO set P is a complete lattice, then after we know that P is a complete lattice, let me just pick up any 2 points x and y belonging to P. Then if we consider the set S, which is the set of these two elements x and y, then obviously this is a subset of P, because x and y are both elements of P. So S, which is a set consisting of these two elements x and y, is also a subset of P. Now because we know that P is a complete lattice, we have already taken that by definition of complete lattice, whatever subset S you may choose of P, the join of S and the meet of S both should exist. In this case, S in particular is the set consisting of two elements x and y. So this means that the join of S and the meet of S in this case will also exist, because P is a complete lattice. Now, but what is the join of S? What is the join of S? The join of S is the join of the set consisting of two elements x and y, or in other words, the join of S is x join y. So this also exists. X join y, this is existing. So this is one thing that we have. And the other thing that we have is that the meet of S, I just emphasize that the meet of S is also existing, because P is a complete lattice. And but what is the meet of S? Meet of S is the meet of the two elements x and y, the set consisting of two elements x and y, which is nothing but x meet y. We can even call it as x meet y. This means that x meet y also exists. So these two statements or these two expressions are true, and this here x and y have been chosen arbitrarily. X and y are arbitrary elements of P. This means whatever elements x and y of P you are choosing, we will always have that the join of x and y will exist and meet of x and y will exist, which means by definition of a lattice that P is a lattice, because the definitions of lattice, the conditions for P to be a lattice are being satisfied. This means that if P is given to be a complete lattice, it will also turn out to be a lattice. So this was one claim that we did, but the result is not true the other way around, which means that the converse of this result is not true. Which means that if you are given a lattice, it is not necessary that it will be a complete lattice. That is not true always. So we can have lattices which are not complete lattices, this means. So let me give you an example of a lattice which fails to be a complete lattice. So if you take the set of real numbers with respect to the usual less than equal to relation, the usual sense in which we understand less than equal to, then we can note that the PO set, this already is a PO set. This again has been discussed in my earlier videos on PO sets. So the set of real numbers with respect to the usual less than equal to relation, where less than equal to stands for the usual sense in which we understand less than equal to. So this PO set is a lattice. Because again, the argument we can give is that if you choose any x and y belonging to the PO set R, then either x will be less than equal to y or y will be less than equal to x. This one of these two has to happen. And if let's say if x is less than equal to y, in that case the join of x and y will be the element which is greater, which means y, and the meet of x and y will be the element which is smaller, or will be the real number which is smaller, which is x. So in any case, x join y and x meet y, which in this case are y and x, are both existing. And if the other condition holds, which means if y is less than equal to x, in that case x join y will be the greater real number, which is greater with the one which is on the right, which means x, and x meet y, this is equal to y. So in any case, whether y is less than equal to x or x is less than equal to y, we find that for any pair of elements x and y belonging to R you choose, x join y and x meet y both are existing, which tells me that this set of real numbers with respect to usual less than equal to relation is a lattice. But the set of real numbers with respect to the lattice of real numbers with respect to usual less than equal to relation fails to be a complete lattice. So the question is, why does the set of real numbers, the lattice of the set of real numbers fail to be a complete lattice? Now the argument that you can give in this regard is that the reason is that the basic definition of a complete lattice is not being satisfied for the set of real numbers, because in the set of real numbers, or in the lattice of real numbers, you do not have that for this condition, which is that for every subset S of R you may choose the join of S and the meet of S, this should always exist. This condition is not being satisfied because if you take S to be Z, the set of integers, then we find that the join of Z and the meet of Z both do not exist in the set of real numbers, in the lattice of real numbers, because there was a video which I made in this regard, that if P less than equal to is a PO set, then the join of P and the meet of P will be given by the top element and the bottom element respectively, provided the top element and the bottom element exist in the PO set P less than equal to. So this result was discussed in detail in one of my videos. So just making use of this particular result, now if we just consider Z as a subset of the set of real numbers. Now I know that the set of real numbers, this is a PO set, and every subset of a given PO set is a PO set with respect to the same order as that of the given PO set. So because Z is a subset of R, so Z less than equal to, that is also a PO set. So now in this PO set, the join of Z and the meet of Z, if they would have existed, the join of Z would have been the topmost element, or the top element in the set of integers, and the meet of Z would have been the bottom element of the set of integers if the top element and the bottom element in the set of integers would have existed. But we find that in the PO set Z less than equal to, there is no top element. The top element doesn't exist. Why it doesn't exist? Because there is no integer which is greatest of all integers. There is no such integer which is greatest of all, which means that the top element, or capital T, in the set of integers, or in the PO set of integers, doesn't exist. By a similar argument, the bottom element, or the inverted T, this does not exist in the set of, or in the PO set of integers. Why? Again, because the bottom element is the element which is smallest of all, and there should be an integer which is smallest of all the integers. But then in the set of integers, there is no such integer which can which is smallest of all the integers. So such a element doesn't exist in the set of integers, which means that the bottom element or inverted t doesn't exist in the set of integers, which simply means that the join of z and the meet of z, these do not exist. And because they are not existing, this means that we have found out a subset S of R, namely S is equal to Z, the set of integers in which the join of S, or we can say that the join of the set of integers and the meet of S, which is the meet of set of integers, both are not existing, which means that R less than equal to, which was a lattice, this fails to be a complete lattice. Now in this particular example, in order to show that the lattice of the set of real numbers, this is not a complete lattice, the subset that we have taken, the subset S of R that we have taken, was the set of integers. But the same argument could have been given if we would have taken Z to be, let's say, the set of natural numbers. Again, the argument remains the same, because there is no top element, and of course the bottom element is there, because the bottom element of the set of natural numbers is 1, and the hash diagram, if you see for the set of natural numbers, it goes like this, although this is not a well defined hash diagram because the top element is not there, but the hash diagram looks somewhat like this, 1, 2, 3 and so on. So the top element is not there. Of course the bottom element is there, but then again the set of natural numbers is that subset of the set of real numbers which fails to have a top element, and because the top element is not there, so the join of S, or which is the join of the set of natural numbers, which this doesn't exist, which means that R less than equal to can't be a complete lattice. So this argument could also have been given. In fact, if we treat the set of real numbers as a subset of itself, because every set can be treated as a subset of itself. So if we regard the subset S as R itself, by treating the set of real numbers as a subset of itself, then we again find that the join of R, the join of S in this case, which is the join of R, the join of real numbers, and the meet of S, which is the meet of the lattice of real numbers, both are not existing, again for the simple reason because the set of real numbers doesn't have a top element, as there is no real number which is greatest of all real numbers, and because the set of real numbers doesn't have a bottom element which is inverted t, just because there is no real number which is the smallest of all real numbers. Since these two elements do not exist, so join of R and meet of R cannot exist, because again I refer to that the result which I discussed in the video, that if p less than equal to is a PO set, then the join of p has to be the top element, and the meet of p, this has to be the bottom element, the inverted t, provided the top element and the bottom element both exist in P. So since in this particular case, in the set of real numbers, the top element and the bottom element are not existing, so R, when regarded as a subset of itself, this doesn't have a join, it doesn't have a meet, which means that R less than equal to cannot be a complete lattice. So the argument can be given by taking S to be anything. S can be taken as Z, which is a proper subset of the set of real numbers, or S can be taken as N, which is again a proper subset of the set of real numbers, or S can be the subset S can be taken as R itself, which is a subset of itself, which is a subset of the set of real numbers. In every case, in using any any value of S, using any S out of these three, or any other subset of the set of real numbers, like set of rationals, etc., we can show that the set of real numbers is a lattice but fails to be a complete lattice. That was the result between a lattice and a complete lattice, that a complete lattice will always be a lattice, but converse need not be true, which means that given a lattice, if you are given a lattice, it is not necessary that it will be a complete lattice. So this is one result that I had to discuss in this video, and also this gives an important observation. From here we get an important observation. That observation is that if we are given a lattice p less than equal to, if p is given to be a lattice, and we find that p fails to have a top element, or it fails to have a bottom element, or it fails to have both top and bottom element, in that case you can immediately conclude that this lattice cannot be a complete lattice. Because for a lattice to be a complete lattice, both top element and bottom elements are required. And why are these top elements and bottom elements required for a lattice to be a complete lattice? Because if you regard P as a subset of itself, if you regard P as S, that is a subset of itself, then since if P needs to be a complete lattice, then the join of S and the meet of S should exist for every subset S of P. In particular, for S is equal to P also, the join of P and the meet of P should exist, which means that, in other words, the top element and the bottom element should exist for a lattice to be a complete lattice. So if we find that, if we are given a lattice, and if we are able to find out if one of them is missing in a lattice, whether the top element is missing or bottom element is missing, or both are missing, if you are able to find that by critical observation or by looking at the hash diagram of P, then one can immediately conclude that the given lattice will not be a complete lattice. So that was all about what I had to discuss in this lecture.